Hello everybody. This is Ioan Raicu. I am a faculty member at Illinois Institute of Technology in the computer science department. I'm an associate professor, and I work in distributed systems. So today I will be talking to you about some of the research that I'm conducting in my lab and how we're taking advantage of a very unique resource called the Mystique Programmable Testbed to conduct this research. So let me give you a high-level overview of the research lab that I run, the Data Intensive Distributed Systems Laboratory. So we conduct research in the design and the implementation of distributed systems. Within distributed systems, we've focused oftentimes on issues such as scheduling, application scheduling, storage. How do you manage storage? How do you, for example, couple application scheduling with storage? We've built file systems. We have built runtime systems. Alright. So let me show you some of my students, at least from last year. So this was a picture of some of the students, and we've got a good mix of students, from undergraduate students that you see here in the middle to master students on that side, and then PhD students on this side. So, alright, I would also like to acknowledge various funding sources. So we've had the National Science Foundation and the Department of Energy fund a lot of the work, NASA as well. Industry such as NVIDIA, Mellanox, and Intel have funded some of the work that we've done as well. And we have also had infrastructure support, such as access to big computers from Amazon and Argonne National Labs and Microsoft Azure and several other large. Okay, so here is the overview of my talk today. So it's split over into 4 parts. They're not going to necessarily be equally broken out, but there are 4 distinct parts to the talk. I'm going to first tell you a little bit about this Mystique testbed that I alluded to in the title slide. I will then cover 2 different projects, research projects that we have ongoing in the lab that are making use of this testbed, this Mystique testbed, and then I'll wrap up with various research and educational activities that I have been involved with as synergistic activities with the other duties that I have, such as teaching and whatnot. So it's yeah. So let's get going. Let's talk about Mystique. So, what is Mystique? Mystique is this NSF-funded infrastructure grant that we received several years ago for about $1 million. And what we promised to do in this proposal was that we were going to build an experimental testbed that will be highly configurable and that will allow systems researchers, such as myself and my colleagues and others, to explore a variety of research topics that simply cannot be done on existing infrastructure, such as, for example, Amazon, or if you go to a large computational center from Argonne. Although you might get access to very interesting hardware, typically you don't have the system level access that you need to, for example, design a new operating system or look at scheduling algorithms for the operating system, or things that are so low level that are typically not accessible to a user when they use these large machines. Okay, so in a nutshell, Mystique is essentially a relatively small testbed, but has some unique properties that make systems research, very interesting systems research, quite viable and possible to be conducted on this testbed. Okay, you know, a picture's, you know, I like the phrase, the picture's worth 1,000 words. So here is a picture of the Mystique system. It's a 3-rack system, so each of these is a rack. And if you've never seen a rack in real life, racks are, you know, about 6-7 foot tall, and I believe like 3 foot wide or so. So that's what each of these racks represents. We have about 55 computer systems inside of these 3 racks. For example, I wanted to mention some of the other people that are involved. We have Kyle Hale and Zehe Sun, who are also faculty members at IIT. One more person I think is I really wanted to mention was Alex Orhian. He's the main system administrator for this Mystique system. We've had so let's get down into the details of what Mystique has. So besides the 3 racks, which I've already told, the 55 nodes, it consumes approximately 45 kilowatts of power when it's all turned on and running. So essentially looking to deploy OpenStack, which is a cloud, open source cloud software that allows us to manage all the computers with bare metal provisioning and with virtualization, and we are pretty close to having that complete, which at that point we could have very easily add additional users that would manage their own resources through this OpenStack interface. So yes, all right, so let's look at what kind of aggregate resources do we have. What we have here is we have lots of compute resources on the order of hundreds of teraflops. We have terabytes of memory. We have hundreds of terabytes of storage, and we have a 100 gigabit network interconnect. Now these are all very broad terms, and they're spread out over the 55 computers. So let's talk about each particular individual computer and how they're interesting. And perhaps what makes them most interesting is the fact that they live under one roof. So you can conduct experiments to compare things back to back. All right, so let's start off with one of our more interesting systems. This is a single computer system that has 8 sockets. So it's got a shared memory architecture with 8 processors from Intel, and it's split up over 8 blades, where each blade can have storage, and it has GPUs and lots of memory and lots of cores. So if you look at the system, this is actually a when we procured the system, we were thinking about what might a computer look like in 5 to 10 years from now. Not any computer, but like a standard server that you might buy. And if you've been keeping up with the trends on how chip manufacturers like Intel and AMD have been adding more and more cores to their processors, you've probably realized that over the last 20 years we've been having this exponential growth of number of processors on a chip. So we went from about 20 years ago, we only had one processor, one core on a chip, to today where we have 32 cores on a chip, even 64 cores on a chip. So it might be plausible that in the next 5 to 10 years that we might have hundreds of cores on a chip, or maybe thousands of cores on a chip. It's quite possible that this trend will continue for some time. Maybe not at the same pace it's been advancing over the last 20 years, but nevertheless, we expect to get systems with more and more cores over time. So let's look at some of the storage hardware that we have that is quite interesting. So if you've I'm sure many of you know that that hard drives are slower than memory, right? Well, what if I told you that that it's possible to build storage systems today that are almost as fast as memory? So here's an example of a machine that has 32 hard drives. So the hard drives go in these little caddies. So there's 32 hard drives that you could put inside of this one system. And each hard drive can do about 2 gigabytes per second. So if you take 32 times 2, you get about 64 gigabytes per second. Well, if you benchmark the memory subsystem of this machine, this has 2 processors, you know the memory subsystem is probably only about 100 gigabytes per second. Yet the storage, the hard drives can drive almost half of that speed to the hard drives and back. So then the next question is, what would you need hard drives that are so fast for? Well, we'll talk about some of that. However, keep in mind that the cost of hard drives per gigabyte is a lot lower than the price of memory per gigabyte. What kind of hard drives do we have in here? By the way, we have these Intel Optanes, which are quite interesting. They do not require lots of concurrent operations at the same time to get peak performance of the system. So very interesting set of technology from Intel. We also have. Let's talk about accelerators. So we have several different types of accelerators. GPUs. We have both older NVIDIA K40s and newer NVIDIA V100s. So we have different types of systems, but here's one example of a system with 8 GPUs. These type of resources are excellent for example for deep neural networks. So people that want to train neural network models and you want to train them fast, you give it one of these systems that has 8 GPUs, and it's not just 8 GPUs, but each GPU has 16 or 32 gigabytes of memory, and so you have 8 of them. The system might have hundreds of gigabytes of memory, and all of a sudden you've got a machine that can, take some of the largest neural network models, think like ImageNet, and you can train those kind of systems from scratch in a matter of hours or days. Where if you didn't have this kind of a resource, and let's say all you had was a laptop, it probably would never completely train with that much data, where you have millions of images and millions of parameters inside of the neural network. So, okay. And the whole thing is connected over this Mellanox 100 gigabit Ethernet factory topology. Each rack has its own switch, and then the switches are connected over a factory topology. The outside network connectivity is only 10 gigabit, but internally between the nodes we have this 100 gigabit network. So all very exciting, very cool. It's a system that that over the last 3 years has cost about $1 million to build, and it's enabled some very exciting research that I'll be talking about shortly. As a summary, we have all the major computing architectures that are off the shelf that you could go buy. Things like x86, ARM, Power9, and then on the GPUs we have from NVIDIA, we have several different generations of NVIDIA GPUs, and also from Intel we have the older Xeon 5s and then the newer FPGAs. The systems that we have a variety of architectures from 1 socket to 8 sockets. Alright, so this work is spearheaded by Purnima Nukala, who's one of my PhD students, and it's in collaboration with Peter Dinda from Northwestern and Kyle Hale from IIT. Alright, so let's talk about this XTask system. So let's talk about a high-level overview motivation of what this work is really about. So it's primarily motivated by an ever-increasing amount of parallelism that exists on computing systems. Over time, we've been as manufacturers have developed bigger and bigger processors with more and more cores, created a bigger and bigger challenge for developers to make use of all of that parallelism, all of the cores that are available to an application. One method of extracting and mapping applications and computations onto a multiple core processor architecture is through tasks. So task parallelism, where you decompose your application into individual tasks, becomes important to support efficiently. One way to implement task parallelism is through OpenMP. So OpenMP is a parallel runtime extension to the C language, which is very popular in scientific computing, and it tries to hide a lot of the complexities that programmers have to deal with when they have to take an application or an algorithm and parallelize it across multiple processing cores. Kind of the programming model, this OpenMP programming model, things like task parallelism, that we want to have applications broken down to individual tasks, and then how do we manage these tasks? Well, oftentimes they're managed via some queue. So there's an in-memory queue that tasks get placed in. These tasks then get pulled off the queue, executed, and the queue acts typically as an intermediary between, say, the compiler and the high-level programming language, and the individual tasks that were decomposed into small pieces that are going to run across multiple cores, multiple processors. So there's these queues can be implemented in multiple ways. There are in the simplest case, we have single producer, single consumer queues, what we call SPSQ. These queues typically are very easy to implement. I'm sure many of you have implemented them in your data structure class as an undergraduate student in computer science. So nothing fancy. The single producer consumer queues are exactly that. They only allow one process to really enqueue or dequeue things from the queue and off the queue, and that's what makes them easy to implement and really it also makes them very fast. So there is no support for multiple threads or to be interacting with the queue at the same time, which is where this other one, the multiple producer, multiple consumer, comes in. So if you wanted to share a queue across multiple threads, you would need to coordinate access to, for example, the head of the queue and the tail of the queue. So you can implement these multiple producer, multiple consumer queues with synchronization mechanisms, with things like mutexes and semaphores, and we'll talk about some of those in a bit. The first motivating example that really is at the core of this XTASK project. So remember I said that you have queues, and you can implement queues with a single producer and consumer queue. That's the most simple basic queue that you can have. It has no support for concurrency, so you can't have multiple threads interacting with this queue. So let's look at the performance of this single producer and consumer queue. So what we have here is we have the latency and the throughput. So let's do it one at a time. So let's look at the latency. And what is latency? Latency is the cost, the time that it takes for an enqueue operation or a dequeue operation. And I think here we might have actually done an average of enqueue and dequeue. So, and we picked 5 different systems. They're all relatively high core counts. 64 cores, 96 cores, 40, 64, 192, and they're different architectures. You know, we have the AMD x86, ARM, Power, PC, and x86 Intel. Okay, so very wide variety of hardware. However, what I want you to really come away from this figure is that the latency of this very simple single producing consumer queue is actually very low. Okay, the fact that we could do within 30 cycles or 40 cycles an NQ or a DQ means that this has got to be pretty fast. Remember, you have 1 billion cycles in a gigahertz. Let's look at what does that mean for throughput. So latency is low. What about throughput? Well, let's pick the slowest one out of them. So the Xeon Phi. The Xeon Phi is able to achieve on the order of 30 million or so per second. The Epic, about 160 million. And the Skylake, Intel Skylake, over 200 million per second. So, if you think about that for a second, and by the way, this is, remember, single producing consumer, so there's no parallelism here. We're really using only one core of 64 here, or one core of 192 cores. Okay? So, very low latencies, on the order of 30 to 70 cycles, and pretty high throughput for one core, only one core out of the whole system, on the order of tens to hundreds of millions of operations per second, NQs or DQs. As we come to some other graphs that will show you the impact of synchronization mechanisms. So what are these? So mutex, semaphore, spin locks, atomics. These are synchronization mechanisms that are necessary to allow multiple threads to interact with a shared piece of memory. What is being shared? The queue. Well, not all the elements of the queue necessarily, but the heads and the tails. So without further ado, let's look at some of these results. So before we really dive into them, I want to basically point out that, you know, we have the 4 different approaches: the mutex, the semaphore, the spin lock, and the atomic operation. And we have a dozen or so systems that we tested on. So this is not an issue that happens on one system. It actually happens across any of these systems, across any architecture. Let's look at one of them a little bit closer. So let's look at the mutex. This is the one that allows you kind of the binary two phases, either lock or unlock. Notice that the fastest possible speeds at only one thread, that's the equivalent of the single producing consumer thread queue that has only one thread. And you put a lock on it. You put a mutex around the head, put a mutex around the tail. There's no contention because there's only one thread working on it. But it still has to go through the process of getting the lock and releasing the lock. Remember the times that we had before the cycles? They were all 30 to 70 cycles long, which would have been here. Notice that right now these systems all have, even on one thread, they're all in 100 to many hundreds of cycles, which is what these numbers represent. And then as we add threads, this is 2 threads, and this is 4, and 8, and 10. Notice the linear increase in time. So by the time we hit about 10 threads, they're all about 1,000 cycles. And by the time we hit 100 threads, they're all about 10,000 cycles. And by the time we hit several hundred threads, they're reaching on the order of 100,000 cycles. So what used to cost 30 cycles, now all of a sudden it costs almost 100,000 cycles. So that is many orders of magnitude higher cost. And that higher cost is coming from the contention, right? From the fact that all of these hundreds of threads are all fighting for the same lock, trying to acquire it. So we can basically conclude that none of these mechanisms really scale. What happens when we put these synchronization mechanisms then to implement a queue? So we talked about the single producer and consumer queue at the beginning, right? And that was the really fast one. Well, we were curious about the synchronization mechanisms because we wanted to use them to build a multiple producer and multiple consumer queue. And this is what happened when we took those synchronization mechanisms and we implemented a multiple producer multiple consumer queue with kind of the best known technique that we could think of, which was the atomic operations. Notice that our latency all of a sudden is not in the hundreds of cycles anymore. Okay, the bottom here starts at about 1,000. So even on a single thread, it costs several thousand cycles to do an NQ or a DQ. And you might ask, but it used to be hundreds. Why is it now thousands? Well, the thing is that an NQ is not just a lock, get the lock, or set the lock, right? An NQ has several different memory accesses, it modifies memory, and it has to deal with locking and unlocking. So there are several different operations that have to happen for an NQ to be successful or a DQ to be successful. Which is why the bottom, the fastest possible times are somewhere on the order of about a few thousand cycles. And then everything is shifted over by one order of magnitude higher. So, at the largest scale, for example, this one with 192 cores, it's exceeding hundreds, 100 to 200,000 cycles for a single NQ or DQ. And you might say, but you have lots and lots of cores, right? You have 192 cores in the system. So even though it's really slow per core, but you have a lot of cores. So maybe it still behaves fine, right? Maybe if we run this benchmark and we run the experiments over lots of cores, we will still get very good performance. And that's what the throughput tells us. So if you guys remember, we talked about the single producer and consumer queue, the really simple one with no locks. You guys remember the numbers, right? They were in the tens of millions to hundreds of millions. So the Intel Skylake 192 system had almost 200 million tasks NQs or DQs per second. That number is down, it's the light blue, it's down to about 1 million. And all of that on a single thread. All of that came down largely because of the cost of synchronization. And then you say, well, okay, but there's 192 cores. So maybe if we have 1 million per core, as we add cores, maybe this is going to go faster. Maybe we're going to get more throughput every time we add a core. Well, every time we add a core, we get performance improvement for a little bit. So I believe this is 2 cores, 4 cores, 8 cores up here. So up to 8 cores, we got good improvement. We went from like 1 million to, I don't know, about 5, 6 million. But then, look what happens. The performance, this is the aggregate performance. So essentially, as we add more cores, the throughput starts to drop. By the time we hit 100 cores, we're back down to 1 million per second. This is 1 million across 100 cores. That means that each core is only getting like 10,000 per second. And as we keep going, we're down even further by the time we saturate the processor. So, so we took this single producer, single consumer queue that was extremely fast on one core, hundreds of millions per second on one core. When we run it across lots and lots of cores, what do we get? Less than 1 million per second across all the cores of the system. Boy, so instead of gaining performance as we add more and more concurrency, more and more processors, we have lost orders of magnitude of performance as we went from 1 to 192 core system. We started with the premise that that very simple single producer single consumer queues are very fast, but they're not safe to be used in a multi-threaded environment where you have multiple cores and multiple threads. So what if we could take this idea of a single producer single consumer queue and use it to emulate a multiple producer multiple consumer queue? So we're not actually implemented, because if we were to implement it for real, then we would have these synchronization mechanisms, which we've already seen are not scalable. But what if we could use it to emulate this multiple producer multiple consumer queue? And you might say, well, why do we want to emulate it? Well, the programmer doesn't want to deal with hundreds of queues or thousands of queues, right? The programmer just wants to enqueue something and then dequeue it later, which is the illusion that there's only one queue. However, underneath the covers, you could implement that single illusion of one big queue with lots of individual smaller queues that can limit the concurrency. It can limit the fight over a single lock, because you might have more locks. You might, perhaps every queue has its own lock. And not only that, but we believe that we could get rid of locks altogether if we're going to focus on essentially implementing these queues as single producer, single consumer queues. So that was the key observation that we made, was that we would try to build a multiple producer, multiple consumer queue with building blocks such as single producer and consumer queues that have eliminated locks and have been implemented in such a way that can guarantee that there's only one thread at a time really interacting with any of these queues, which then makes them safe to be used in a multi-threaded environment. So, all right. So here's a diagram that shows you how 4 cores, your lower core 1, core 2, core 3, and core 4, what a 4-core setup would look like. And essentially, you would have, each core would have its own master queue. And then there would be 3 auxiliary queues, which, if you follow the dotted lines, each of these queues goes to a different core. This has the potential to have an explosion number of queues, right? With 4 cores, you end up having 4 queues per core, so you have 4 times 4, so you have 16 queues. Well, if you have 192 cores, it's 192 times 192. The good part that these queues are actually pretty lightweight and they don't take a lot of resources. So the amount of memory that is being consumed by, describing the queues, like the head and the tail and these kind of things, it's actually pretty small. Each of these queues can be implemented with a single producer, single consumer queue, which means that they need no locks, as long as you can guarantee that only a single thread will ever access the head or the tail of these queues. The idea that we could take this single producer, single consumer queue with no locks and no synchronization mechanisms and use it as a building block to implement essentially something that looks like a multiple producer, multiple consumer queue. Okay, so the last thing that I wanted to mention is that a lot of the systems that we have today, and especially in the Mystique system, have multiple NUMA zones. Typically every socket has its own NUMA zone. For the Intel processors, for the AMD processors, there's several NUMA zones per socket. So for example, the AMD EPYC system has 2 sockets with 4 NUMA zones per socket, so there's 8 NUMA zones in total. So the different NUMA zones means that you're going to have different latencies to memory across these NUMA zones. So we found that trying to map the topology of the XQ system, where how the queues are distributed across all of the cores, and having that topology be mapped to the NUMA zones actually helps performance quite a bit by constraining communication between cores within the NUMA zone and trying to limit cross-NUMA zone communication. So bigger obstacles that we've faced was the idea that the fact that we had all of these auxiliary queues, that we, under certain conditions, that the system would have to check multiple queues before it could actually advance to the next operation. And remember, we have n queues, where n is the number of cores in the system. So, so there's a trade-off here, right? I mean, if you had a lock, you might have multiple threads fighting for our lock. In this case, we don't have locks, but you have multiple queues, and you have to go and check multiple queues for one operation. So, so to some degree, as you add more and more cores, this approach, will have its own limitations, because the cost of accessing all of these different queues increases with more cores that you have in the system. So we'll see some evidence of this as, for some of the workloads, how this checking of the different queues becomes potentially a bottleneck. So let's look at how XQ performs, and we did this across all of the different systems we looked at earlier. And essentially here we are looking at latencies of NQs and DQs and within the XQ system. Now, one of the things that I think should be striking very early is that the cost, the latency cost, looks pretty fixed. Now, I know it looks different across different systems, but take one system in particular. You take this system, and the latency cost is about the same. Take the red line, it looks about the same. Take the yellow line, it looks about the same. So, so we were quite pleased with the idea that although the latencies increased, they were not 30 to 70 cycles anymore. They're now 100 to 400 cycles. But remember, we're doing, we have all these different queues that we have to check. There's certainly a lot more work to be done, and we're doing this across many threads and across many cores. Before, the single producer and consumer queue could only work on one thread at a time. So, so at least from a micro benchmark perspective, the exercise was a pretty good success. If you remember, the multiple producer, multiple consumer queue had data that looked like this, that had linearly increasing latencies as you added threads. Now, the data looks flat, which is actually the ideal case, where essentially it shows that that we can very scalably implement something that looks like a multiple producer consumer queue, but yet it uses building blocks such as single consumer, single producer queues underneath the covers. So, all right. So, how does this impact throughput? So, right. I mean, if you had a very good scalable system from a latency perspective, then we would expect that the throughput would actually look great. So, let's look at the top line here, which is really what what XQ's performance is. This is on the 192 core system, and notice that this is million, 10 million, 100 million. So we could basically get performance from 100 million up to about 1 billion NQs and DQs per second using this kind of single producer and consumer queue underneath the covers, which is great. Remember, before, the purple line is actually the line that we showed early on, which essentially shows that we could only do 1 million or so operations per second. So even a single thread has 2 orders of magnitude improvement, but as you go into really large core counts, we have 1, 2, 3, almost 4 orders of magnitude increase in performance. All right, so then the next part was, okay, so we managed to do one micro benchmark. So let's put it all together into, how does this impact real applications? So we went to OpenMP. OpenMP being one of the most popular high-performance computing systems to implement parallel applications, and we went and modified the runtime and replaced the current approach, which basically has multiple queues with locks and with atomic operations. Actually, not with locks, but with atomic operations, and replaced that with the XQ system, which basically got rid of the locks and added n queues per worker. We needed the n queues, if you remember, for load balancing purposes, while the traditional OpenMP only had one queue per worker, and it used work stealing to do the load balancing across the different workers. So once we made the modifications to OpenMP, we looked for applications. So what applications could we target? Now remember that one of the things that we were targeting were applications with fine-grained parallelism. So we needed applications that had very small amounts of work per task. So we looked at the TP parsec benchmark, which has a variety of different applications, and there's about 13 different parallel applications. And we settled on two different applications. One is the Fibonacci, computing the Fibonacci number, which is nice because it has very small fine-grained tasks. The leaf task being just an addition between two numbers. And then this Black-Scholes application, which I'll talk about in a bit. Okay, so one of the applications, one of the benchmarks that we picked was the Fibonacci benchmark. I'm sure you're all familiar with it. The interesting thing that it can generate extremely fine-grained tasks, because the tasks after the recursion call and you get to the base case is basically just the addition of two numbers. So it generates lots and lots and lots of tasks, and each task is very small and fine-grained. So it puts the biggest pressure on the runtime system that is managing those tasks, and allows us to evaluate its behavior. So that was one application. So let's look at the kind of performance improvement that we were able to achieve. Essentially, as we increase the number of cores from 1 to 192, we get a particular speed up in performance. Notice that the speed up is not linear. I mean, we only have about 30x speed up for a 192 core system, which it comes from the fact that these tasks are so fine-grained, so small, that getting good performance out of the system, kind of linearly increasing, is not trivial. And essentially, what we were able to show is that if we run OpenMP natively without any modifications, we get the light blue line, which basically shows that the XQ approach, where we can support these very fine-grained tasks, we can actually get a sizable increase in performance. With larger the scale, the bigger the increase in performance, until towards the very end, where the improvement is more modest. So overall, we get a 2 to 3x speed up in performance. Now, let's back up for a second. Remember, we talked about XQ running many orders of magnitude faster than the traditional approach of implementing these queues, these multiple to small consumer queues. So what gives? We have thousands, tens of thousands x improvement in throughput of performance of these queues, yet underneath the covers we only get 2x or 3x performance improvement, which is still great, but is nowhere near what we expected. So part of the problem is that running a parallel application through OpenMP is not as simple as just enqueuing and dequeuing some tasks. So sure, that's part of managing these tasks, but there's a lot more things that are happening under the covers. So for example, the task creations within OpenMP is relatively expensive, and every time there's a task, it needs to be created. So the creation, from everything we've seen so far, the creation of tasks largely overshadows the cost of managing these tasks throughout their lifetime, given that these tasks are very small and fine-grained. Therefore, since our work only looked at managing the tasks and not changing how we're creating these tasks, the amount of speed up that we got was more modest. If we look at the Black-Scholes application, this was a little bit closer to more of a realistic application. It looks at computational finance, and it essentially looks at solving differential equations. And in our particular case, we had a loop of 10 million options that were repeated a bunch of times recursively, and let's look at some of the results. So the results were not as impressive as the Fibonacci numbers, yet there was still some improvement in performance. The A&D system got about a 10% boost. The Skylake system managed to get anywhere from just a little bit faster to about 2 times faster, kind of in this region of the code. It all came down to really understanding where the different costs are. So one of the big costs seems to be within OpenMP about creating tasks. So that's going to be our next step in trying to improve. Perhaps just like creating threads, for example, is very expensive, creating tasks is also very expensive, and it seems that the default, the de facto way of managing these tasks is to create these tasks every time that they're needed. But you have to remember, when you create tasks, you have to do mallocs, so you have to allocate memory, you have to potentially free memory when you destroy the task. So all of those types of operations can actually be very expensive if the amount of work you're doing is very small within a single task. So we think that these numbers will be able to actually get a lot better as we look to make further improvements to OpenMP's runtime system. All right, so overall, I think if I were to summarize our work on XQ, what I can say is that for micro benchmarks, we've been able to get really great speed ups, many orders of magnitude better performance. We've shown how the XQ approach can improve OpenMP's performance, which basically opens up the door to many different applications that could use XQ without modification. So that would be a step in the right direction, and we're looking at potentially how to take these kind of speed ups that are currently modest, only 1.5, 2x, 3x, up to maybe tens or hundreds of times faster, getting things closer to what the micro benchmarks actually show. Yeah, so I think there's still a lot of performance being left on the table in terms of building really efficient, lightweight runtime systems for fine-grained tasks. We still have a lot of work to do, and a lot of different applications that we'd like to explore. For example, Tensorflow is another application that has extremely fine-grained tasks. Think about the operations that are happening inside of the tensor core. It's basically a 4x4 matrix multiplication, which is in the big scheme of things, it's actually pretty small and fine-grained. So we're looking at a variety of different types of work where we could apply the same techniques and hopefully get some big boosts in performance. Furthermore, I'd like to loop back to the start of this presentation where we talked about the Mystique testbed. So the study that we've sought out to do with this XTask and XQ system really necessitated the type of testbed that Mystique has to offer. You know, so some of the motivating data that we collected really wouldn't look so startling if we had a small system. If we only had a 4-core, 8-core system, the gap between one approach and another approach might actually not be very big. However, as we saw in some of the cost of synchronization mechanisms, as you go from 1 core to 192 cores, we saw the huge gaps and then the huge potential performance improvements on, you know, when we implemented XQ with micro benchmarks. You know, this was really all possible because of the nature of the Mystique testbed, where we had a variety of different hardware with different types of architectures and different number of core counts, and we were able to have a platform where we could show such big and drastic differences in performance for different approaches and different techniques. So I hope you can appreciate the uniqueness of this Mystique testbed as a platform to conduct this kind of low-level systems research that we talked about today. The next topic I wanted to talk about was XSearch. However, in the interest of time, I won't have time to really discuss it. I do want to point out that, you know, the Alex, who, if you remember, you saw him as assistant administrator of Mystique, he's been working on this problem of organizing data in high-performance computing systems and understanding how to organize it, understanding how to index it, how to search it, how to get meaningful data and metadata out of mountains of data that we have in our storage systems today. So unfortunately I won't have time to talk about it, but we're doing some really exciting work in understanding how to search terabytes and petabytes of data efficiently, and how to index it quickly, and how to build essentially new data structures that can handle concurrency with lots of cores, can handle lots of bandwidth that you have from disks. We have these wonderful storage systems that have 16 and 32 drives per node with tens of gigabytes of bandwidth of disk I/O per second. So we're looking at leveraging lots of cores and lots of disks in building highly optimized data structures that then can be used for as a building block to search systems. Yeah, so this will have to be the topic of another presentation. Let me move on into the final part. So I want to spend the last few minutes of this talk to go over some of the educational focused activities that I am involved with. You know, really, it's been overwhelming positive experience for me with, you know, I mean, if you look at it, about 1,500 students from teaching, and, you know, well over 100 students, you know, maybe 150 students or so that I've engaged through research activities over the last decade. So, I have one structured undergraduate research activity that we run this program called Big Data X, and it's an RAU, a research experience for undergraduate students. We've been running this since 2015. Unfortunately not this summer because of the pandemic, but we've been running it every summer since 2015, where about 10 students come in from all over the country, domestic students, and they work full-time in the lab on a research problem. We have several different mentors. and the students really come away with a great experience. You know, we have you know, this is a group of students. I think the first one we had in 2015 when we visited Argonne National Labs. You know, this was in 2016, 17, 18. This is visiting Argonne National Labs inside the machine room, and then the picture from last year. You know, but really a great group of students who learned a lot about research and about distributed systems and about big data. And many of these students, you know, found that they liked research, and they continued with more research by going to grad school, continuing with PhD degrees, or getting jobs at in research laboratories. All right. Another activity that we've been very successful in engaging students with is, and these students have been everything from high school students to undergraduate students, has been the Student Cluster Challenge. This is basically a competition where students are training for half a year to a year, and the competition itself is about a 48-hour competition, 2 days where they don't sleep much. They, you know, and they're essentially, you know, they work as a team. It's a team of 6 students, and they work their way up by building a cluster of computers, and they have a power budget. They, you know, and they have to manage these computers. They have to tune the computers, the applications that run on them. So they have several high-performance computing applications. The hardware is typically very cutting edge. Every year we've run this. The hardware was about $250,000, and the students had exclusive access to the hardware for 6 to 9 months to be able to learn how to use it and learn how to tune and run these applications, so that during the 48-hour competition they could do this successfully. So quite an exciting set of activities here, where we had you know, students. This was in 2014, 15, 17, and 18, where we had these group of students that had a blast, I think, participating and learning a lot about distributed systems. All right, another activity, I think that which I think at DePaul you have a local chapter as well, a UPE, Upsilon Pi Epsilon chapter for the Honor Society. If you haven't heard of it, look them up. I know they've been doing a lot of activities at DePaul, and we've done same thing at IIT. And we've had good success in attracting the top students in the computing discipline and running all sorts of activities, such as, for example, visiting local startups, you know, running workshops for the younger students, like the freshmen, about, you know, what life is like as a undergraduate student at IIT. So all sorts of activities like that. You know, definitely get involved if you can, or if you are a member of the UP, look at what activities that your honor society is doing. It's you know, it's a very worthwhile and rewarding activity. All right, I think the last thing I wanted to point out is, you know, a lot of the work that I've been involved in actually has quite a few collaborators from lots of institutions, both within IIT but across other institutions in Chicago, and a bunch of national laboratories from Argonne to Los Alamos, and so forth. So, you know, and this doesn't include the students, which I mentioned earlier. So really, much of the work in the building blocks leading up to the work that you saw today was not a one-man show myself, but it was really collectively done with lots of collaborators and lots of students. And of course support from the National Science Foundation and industry partners, and so yeah. All right, and then I think the last slide is has a lot of URLs to online information, where you can find things like more information about myself or my laboratory. We have all the publications from the students there. We have the Mystique system, plus our Honor Society, the summer program, Big Data X, and then more information about myself. So It's been a pleasure to talk to you about the research that I'm working on, and I hope to hear from some of you that maybe you're excited about using the Mystique system or about some of the research work that we're doing. If you have any questions, please feel free to reach out to me at the address that you see up on the screen. All right, thank you so much, and we'll hopefully next time we'll see you in person. All right, bye-bye.